Okay. I'm going to talk about the origin of the moon, and the work I'll present is a paper I've written with Matya Chuk. So in case you didn't know, there's a problem with the origin of the moon, and Jay Milosh dubbed it an isotopic crisis because the lunar isotopes, as we measure more and more of them, are identical to the Earth. And the canonical giant impact formation model makes most of the moon out of the thing that hit us. And the isotopes that have been measured, at least these four, have very different isotope ratios in different planetary bodies, mostly the meteorite collection, Mars, and the Earth-Moon system. Silicon and neodymium are identical, but people argue about whether or not those are actually signature isotope ratios for different bodies. And it's gotten to the point where Annual Review's commissioned an article to discuss the problems with the formation of the moon. So the standard giant impact model that most people think about these days are a series of papers with Robin Canup and the first one with Eric Asfog, which has the Mars-size impactor about 10th the mass of the Earth, impacting the Earth at about escape velocity at an oblique angle. And the model was constrained by the present-day angular momentum trying to get the correct mass in a disk around the Earth that then forms the moon, and the low iron content of the moon, which has a core that appears to be about a few weight percent. And where I'm going with this is we're going to propose a different formation scenario where we allow the impact to have a different angular momentum than present day and start with a faster spinning Earth, which has been suggested in some n-body simulations of terrestrial planet formation. When you have a total angular momentum of the impact that exceeds the stability limit of the Earth, you basically have an impact-induced fission that makes the disk mostly out of Earth material, and it's fairly easy to do this with a reasonably fast spinning Earth and impact conditions that we expect at the end of planet formation. 1 to 3 times the escape velocity and an impactor mass usually less than about a tenth the Earth mass.
And Mars is a tenth the Earth mass?
Mars is a tenth the Earth mass. Mars is the magic mass in the inner solar system. It's the isolated embryo mass that the oligarchs grow into, and it's after those bodies eat up more than half of the material in their feeding zones that they start feeling each other's gravitational perturbations to the point where they start hitting each other. And so this one Mars mass is about this oligarchic mass as planets grow. So it was okay that something that size hit us, but there are many more smaller things that hit us near the end. And then, because angular momentum is conserved in the Earth-Moon system, basically, one would have to find a way to remove the excess angular momentum via something that happened after the moon was formed. And here we're suggesting that there was a resonance that could do this. Okay, so we sort of painted ourselves into the corner that we're in with the current giant impact model for a number of reasons beyond angular momentum and isotopes. The mass of the moon is large. Pluto now has 5 moons, and it will have more, right? So Pluto is a different beast as well. Something very interesting happened there. But in the inner solar system, the moon is large. We have this angular momentum that was perceived to be high at the time, and we may not think of it that way anymore. At similar composition between what we had sampled of the moon and Earth's mantle, and similar oxygen isotopes early on was the main thing. And the moon has a low mean density and a small metal core, so one would have to somehow make this planetary body with less iron, or one would have to have some way of separating cores and mantles, which is what a giant impact gives you. And lunar rocks are depleted in volatiles, which points to a high temperature origin, and a giant impact allowed that as well. So the angular momentum, everything in a log-log plot is linear. Angular momentum versus mass from asteroids to galaxies is the same line. Okay, so I don't find this to be particularly meaningful at today, but at the time that people were trying to understand the formation of the moon, they fit a line through the 4 giant planets in the solar system, and Earth-Moon system appeared to lie above it. That's the dashed line. And Mars is roughly on this line, and the other inner solar system bodies are all strange in some way. Mercury is in a resonance, Venus is retrograde, so something interesting happened. And Pluto, Charon at the time weren't being considered. The moon itself just must be different. So there was this perception that the Earth and moon had an excess angular momentum, which I think that, and it could be explained by a Mars-sized body hitting the Earth equator at about the escape velocity is about the same angular momentum. And so this led to the idea that our angular momentum is dominated by this last big accretionary event. And I think one maybe...
It's a clever idea.
It's a clever idea, and a very strong constraint. It ends up being perhaps the strongest constraint on the current moon formation model. And it's just that it may not be such an outlier. Yeah. So this is the canonical model, Mars-sized body hitting the proto-Earth. This is primarily an accretionary event. This is sort of a top-down view and a smooth particle hydrodynamics calculation from Robin Canup's 2004 paper. These are, what did she, this is in thousands of kilometers. And the Roche limit is just inside 20,000 kilometers. And so you want to make a disk that is concentrated near the Roche limit, which is where we think the moon is going to form. And the colors are a proxy for temperature, sort of. Impact, very hot. And because it's an oblique impact, it splays out this spiral arm. There's a clump that in some cases that then re-impacts. There is not excess angular momentum to actually have fission, so what happens in this case is that the non-spherical shape of the Earth during this event torques the debris around it and transfers angular momentum to them such that you have material that has enough angular momentum to stay in orbit when all is said and done. Then you end up with about 2 lunar masses in orbit, and ideally, most of it near or in the Roche limit, because there's very efficient accretion into a moon as material sort of leaks out after that in subsequent simulations that are done of just the moon formation process. So there's this rough factor of 2 times the lunar mass that you need, and the rest of the mass would accrete to the Earth during that process. In many of this standard simulations, much mass ends up much farther from the Roche limit, and some of that presumably would be lost or form other moons that would then interact with each other, and they usually throw each other out. This is the time step view, and this is a side-on view at the end. So torquing to get these spiral arms and disks, and it is a nice flat disk that you can quickly. The time scale for accretion from a debris disk that is all solid is month-ish, very fast. Most people now think that there was a reasonable vapor fraction in this disk that would make it take longer to condense and cool, and how long is a big point of debate right now. So, but in all of these cases, most of this disk around the Earth is mostly made of the thing that hit us. And when Robin, in her 2008 paper, added pre-impact spin, a high impact pre-impact spin that then slows down to the present day value always produced a disk that had too little mass. And so the problem is that we expect a different signature. Right, okay.
And the basis for your problem statement is that asteroids are heterogeneous.
Well, that every other parent body that we have sampled is different except for instantite chondrites.
And instantite chondrites that was the impactor, a giant instantite chondrite. And the moon would be dominated by the instantite chondrite component.
Yes. And then you have to understand what they are and how they're different from the Earth, because they're more reduced, although the moon is not as reduced as instantite chondrites. something else happened to enstatite chondrites. So people, of course, have invoked that you could make the Earth out of a narrow annulus, and then the thing that hit you is just the same thing that makes the Earth, which is a way to get around this stated problem. But most common, the standard model for terrestrial planet formation, considering all of the inner planets, the last impactors tend to come from far away. And if Mars is different from Earth, then one would expect that those impactors, there's no reason to invoke that they should be the same. But views of terrestrial planet formation are changing, where you might argue that material always came from near where we are. And then there's a different problem. This is a model-dependent problem, but the siderophile element distribution in the Moon has a signature that appears to be high-pressure core formation equilibration pressures, which would not be consistent with a small body that happened to be exactly the same composition as the Earth, but just shrunk, that it would then have a different siderophile element abundance. But there is this extra imprint of lunar core formation that's hard to interpret through. But it doesn't seem to be the simple way out. Okay. These are just the isotopes being the same. So let's just skip them because we don't have a lot of time. So solution one to the impactor problem is the most famous. It's a proposal that there was a long-lived lunar disk that hovered at the liquid vapor phase boundary for a long time. And that allowed the liquid in the midplane to mix with the vapor in the disk atmosphere, to mix with the Earth atmosphere, to mix with the magma ocean, such that any initial difference in the isotopic signature between the disk and the Earth was homogenized.
So this is just a cross-section?
This is a cross-section. This is a disk that goes all the way around, like the simulation plots. And in this paper, they argue that potentially you could have up to about 1,000-year lifetime of the disk. And you overturn the mantle very quickly if the Earth is fully melted and turbulently convecting. And the bottleneck is mixing between the atmosphere of the Earth, the silicate atmosphere, because the Earth is boiling, and the silicate atmosphere of the disk, that this is sort of the bottleneck to the process. And there are few very detailed calculations of the disk because it's a hard problem. And most of them are suggesting about 200-300 year lifetimes for a hot lunar disk in the canonical scenario. And it's not clear that that's long enough to totally mix the titanium isotopes that have been measured recently to be identical. It's close, but enough to have cast doubt on whether or not the total equilibration could have been achieved.
It seems that any early formed reservoirs hidden, like Boye and Carlson style, before the giant impact, would have been mixed back into their mantle.
Right. This model basically invokes total resetting of the Earth-Moon system.
Okay. To the depth of the magma ocean, right?
Well, presumably it's the whole Earth because the oxygen isotopes are the same on the whole Earth. And so they have not yet responded to the newest data that came out this year on the xenon and the tungsten, nor on the neodymium aspect of the problem.
It's great for the neodymium aspect.
To homogenize? No, it's not. It's not. So anything that requires preservation of an early reservoir, this is a problematic aspect if you want to have a step that involves total chemical homogenation. And I don't know.
You still end up with this weird scenario where the Earth's oxygen looks exactly like an enstatite chondrite. So it would mean that both of the bodies were a little different from an enstatite chondrite. They hit each other, homogenized to that composition.
Well, there's a lot of special bleeding going on in the inner solar system. So, but this is a solution to the generic problem of the thing that hit us was different, and the data are that we're the same. So a newer model that has not been written down in paper yet, but was presented at LPSC in a couple of abstracts. Well, I mean, that is basically the model. The model, they have a more sophisticated model of the disk where they're tracking it versus time. And so they're letting the disk cool, and they're calculating the material that leaks out, if you pretend this is the Roche limit, leaked out past the Roche limit and then quickly clumps into moonlets and then forms the moon. So they describe the process as multi-stage. Initially, you have the parts of the disk cool quickly and leak out quickly, and they form the seed of the moon. But they will be dominated by impactor material. And then over time, the disk is equilibrating with the Earth, and then more material is leaking out over time. That accretes on top of the material you had before, and the outer part of the moon would look more like the Earth, and the inner part of the moon would look more like the impactor. Okay. So this, of course, requires that the moon didn't remix itself either in its thermal evolution, and that stratification is preserved, and we don't have any samples from the moon that are deep enough to have tapped into that, which may be true when I tried to find the depth of sources for the moon. Most of them appeared pretty shallow. There are some glasses that I don't know about, but
How different would it be compositionally?
whatever you think hit us.
I'm just wondering if you could recite it. Seismically, was it?
Well, there is some stratification seismically. I'm not that familiar with the moon.
But there's core formation on the moon, so at least there's some post-formation differentiation, and that still has, I mean, this is a very new idea, so they have not wrapped it up with all of the chemistry. They're trying to...
Do they give some ratio of the radii?
They do have a ratio of how much mass, and it's a range depending on what you think the properties of the disk are and how efficiently these two talk to each other. Same problem, though. You're still invoking, same problem as before for the Earth part. You're invoking complete mixing with the Earth as part of this.
How deep is the biggest impactor on the moon? How deep would it have excavated into the...
South Pole Aiken goes... It went into the mantle. The hole was sort of third down the mantle, but it only excavated a little bit of mantle material.
But presumably the moon had a magma ocean, but maybe only to a depth of 500 kilometers.
The moon...
So at least maybe the top few hundred kilometers would be homogeneous. So to really test it, you'd have to go beyond that.
Right. The moon, the crust argues for a magma ocean on the moon of some depth, and this would have to be consistent with that. Okay.
So the layering has to be deeper than the magma ocean.
Yeah. So new idea to try and work within the extra constraints of the canonical impact model. Okay. And then the third is basically these special impactors. One is that you're hit by something just like the Earth, except that may not agree with the siderophile partitioning coefficient information that we have. And an idea that was published in an abstract here and seems to be stuck in revision is an icy impactor hit us. And there's less of the silicates from the icy impactor in the disk than in the canonical models, which had 60 to 80% impactor. And now we have a lower number. I think they were working on this before the titanium data, but after the oxygen data. But this is still too much of the other thing, presumably.
So wait a minute. So where did the rest of the silicates go?
They're ice and they're vaporized and they're not part of the moon. So the icy, right, so they either went to the Earth or were lost from the system, because this was a hit and run style impact, and so much of the thing that hit us kept going.
But the point is you need a big impact to make the moon.
You need a big impact to make the disk.
You don't want lots of mass at it, but you want a big impact.
You need to do something interesting to get enough material into orbit. It is a lot of material to get into orbit. And here they were trying to get more from the Earth into orbit, and you could do it with a bigger event to get more energy, more material lofted. It's perhaps one of the least probable impactors to invoke. And it's still, they never found anything that did much better. And I think their paper that I read, the version that I read, had about 30% weight from the other thing.
And the advantage of this model is that we have no constraints on icy body geochemistry.
It's just less than the previous model. So the previous models had 60 to 80% impactor in the disk, and this got it down to 20.
But we can make the composition anything we want. So
It's
this
just-
one has a hidden reservoir, and we've never measured it. The solution 2 had a hidden reservoir at the bottom of the moon.
Yeah.
So hidden reservoirs.
So we still have a problem. Oh, I didn't include one of my figures, but it's too complicated. Okay, so our solution then is the angular momentum is a separate step solution. And I don't have this very complicated figure in here. Instead, I'm just going to show you an example impact. When we're invoking an Earth that's near its spin stability limit, one does not have to have the Earth be actually, this is not losing mass, this is a stable configuration, but it's very close to losing mass. And so it's quite oblate, and it is slightly decompressed. And then we hit it with sort of a typical impactor, less than a 10th Earth mass and twice the escape velocity. And we're hitting it more head-on and slightly retrograde to the rotation direction. And so here we are, we're spinning counterclockwise, and we're hitting it on the side that's coming at us. And the colors denote just the material cores of the two bodies and the mantles of the two bodies. This is the Roche radius, just to give you a sense of scale. And then, and you'll just see where material comes from and where it goes. So it opens a very deep hole in the planet and throws material out. And what we want is most of the material in orbit to be green, since that's the terrestrial mantle. And ideally what you would have is the ratio of red to green, impactor mantle to proto-Earth mantle, to be the same in the disk and the now depleted Earth. These impacts at greater than escape velocity are actually slightly erosive, which is why this particular simulation started with a little bit more than 1 Earth mass. And in this case, I forget, the difference between the two was 6 or 8 weight percent difference in projectile composition. And so we're now in the single digits that you need to satisfy oxygen.
And do you make a moon here? I don't see any moon.
We don't make a moon. None of these SPH simulations make a moon, because we're just making the disk, and the disk has to cool and then form the moon.
But those simulations you showed from Canup and the weather ones always made a little moon.
They have a clump. They have a clump that's a projectile clump, because it's coming in at enough of an oblique impact. It's large enough that it essentially shears off. These are all hydro simulations. Shears off a clump, and that's what you see going around it. That's not the moon. It usually re-impacts. Sometimes there's a clump that ends up in orbit further out. That would not be the main moon that formed from the disk, but would then need to merge or scatter each other off. And so this doesn't have the late time dramatics of the spiral arm and the secondary blob that comes in. What it's primarily doing is blowing Earth material into basically a vapor disk around the Earth.
So where's the disk here, though?
The disk are all these particles. So now the way to think about SPH simulations is that each particle represents a fixed mass whose volume is changing. And the density, I have a density plot in a bit, maybe soon. The density of this material is much less than in here. And so one needs to think of this as smeared out mass and not particulate mass. So I'm making a disk that's roughly twice lunar masses that has enough angular momentum to stay in orbit. And what we were going for were for cases that had mostly Earth in orbit. In this case, it's a continuous structure. It's the solid or liquid Earth grading into a boiling atmosphere, grading into the orbiting disk. Okay. And for a range of near head-on collisions on fast-spinning proto-Earths at this impact velocity range and impactor size, it's quite easy to make disks that are mostly out of the Earth. And then it just depends what you think the impactor is to know what composition you need.
Is the impactor to Earth ratio composition constant across?
It's actually identical for the bound atmosphere and the rotationally supported disk. And the lower part of the Earth that has higher density, that's compressed, is mostly Earth. So yes, so so this is found in all SPH simulations of any moon-forming scenario, that the impactor is preferentially deposited in the outer layers because it's just gravitationally re-equilibrating, and the denser material is sinking, and the most highly shocked material includes the projectile material, and it's rising to the top. So that, and it's the extent of the demixing between those layers is partially artificial from the limitations of the numerical technique.
So to follow up, it looks like here the core of the impactor joins the core of the Earth. I guess we need a little bit of core to stay in space, right?
Yes.
To make the moon's core.
Yes, there's a yellow dot here, for example. But we do not believe.
Yellow dots are good enough.
But we don't believe any of them because we're barely resolved. And so these simulations used 100,000 particles in the Earth. The largest that are run are 1 million particles. It still doesn't give you many of these to track. And once you start having single particles of different compositions in SPH, they're not really behaving as they would. They're not behaving as the two-phase flow they should be. So one essentially is trying to remove the core, knowing that you couldn't possibly have removed all of it. There are many cases where you clearly end up with too much core, and those are more oblique cases, faster spinning, that just tend to have pieces of the projectile core miss the Earth and then go into orbit or get lost. In those cases, you're probably just looking in the wrong parameter space. So most of the cases that have been done in the canonical scenario, and this one, the cores merge into the Earth. And they merge artificially beautifully because, of course, if the lower mantle were solid, then they would not have penetrated so quickly and sunk all the way through. Here, everything is purely hydrodynamic. Okay, and then there's a question of how much chemical mixing happens for the tungsten isotopes. So here's snapshots in time over a couple hours to here, and then this is 2 days later. And this is hard to see the dots, but the blue is the portion of the Earth that has a density of greater than 1 gram per cc. And then the yellow is the bound atmosphere that's lower density. So this is how extended. It's about 1/10 the mass of the Earth that's heated with the equations of state that we're using into a vapor disk. So it is a significant, the boiling portion of the planet. And then the green dots that you can't really see are the disk, the particles that have enough angular momentum so that they do not intersect the Earth. And then here's the density profile through, where the red in the middle is the core, and then the mantle grading by this time quite smoothly into the atmosphere, into the disk. And because this style of impact is different from the Canup ones, instead of a few clumps holding most of the mass, we have a lot more mass in this vapor state in the disk. Some models of forming the moon out of the disk suggest that it's difficult, that instead of accreting a moon, it diffuses outward past the Roche limit, and you never have the gravitational instabilities you need to actually have clumping. And so some early models suggested that you couldn't make a moon if there was too much gas, that one of two things would happen. You would just diffuse away and you wouldn't clump, or you would end up transferring angular momentum and having most of the disk collapse back down. Now that we have more sophisticated models of the disk that have vertical structure in the disk and eventually more radial structure, it seems that we can tolerate more vapor, but it is certainly an issue with whether or not you think you're going to make a moon out of this. No one has modeled this high vapor fraction case. Now, what ends up happening is, this is the density plot again. What you observe with the red points mostly being at the surface is that the hot, highly shocked material ends up on the outer portion of the planet. And so initially we began with a quasi-isentropic planet. And the core here is dark because this is per kilogram instead of per mole. So the core is dark blue. And then we initially had a quasi-isentropic planet of about 3,000 joules per kilogram per Kelvin. And so we've shocked everything. And the bits that are vapor atmosphere out into the disk have extremely high entropies to the point where they're mostly vapor. And then the mantle is a slightly darker blue at the bottom and a slightly lighter blue at the top. Now, we're not going to believe these numbers precisely because this is a very simplified EOS, but it does demonstrate how stratified the Earth is with the outer fluid layers dominated with most of the projectile material added compared to the lower Earth layers. And when we look at where the material came from and where it ends up, here's the after plot.
Back one for a second.
Sure.
I think I'm missing completely the point on the right. Isn't that basically a map of density too?
Yes, it's entropy, density if it's all the same material. Well, it's pressure. There's a pressure term in there that you have to add in your head to interpret what's going on here. And so instead, if you prefer to think in just pure entropy, we've gone from an isentropic planet to a very stratified planet. That's all. So now we were on a convection isentrope, and now we're not.
So one thing I'm sort of not quite getting is, because it's really a continuum, right? From density decreasing outward.
Yes.
But then you make the distinction between the atmosphere and the disk, right? I mean, that's how...
I define different reservoirs in the post-impact planet just to have names for them that correspond to things that we're familiar with.
Okay.
But basically what I'm trying to say is that convection would not be vigorous and turbulent immediately following the impact, that you would have to mix this away some other way before you then have very significant radial mixing. And so this is something...
I'm not worried about the mixing right now. I'm worried about... I guess I'm asking about how you will distinguish what becomes the solid planet from its atmosphere and from the part of the disk that's going to end up being the solid product, right? Because it seems like you have a distinction. You have to have sort of an empty space in between, like something where
eventually,
you only have
yes.
vapor. So how do you get that?
Right.
Is that some natural centrifugal process or what?
So as the whole system cools, the silicate vapor atmosphere will collapse. The disk will cool onto its midplane, and material will be transferred out and inward to conserve angular momentum. And you shouldn't think of it as an atmosphere compositionally different. This is just phases, from condensed phases to gas phases in this structure.
Right, which with a gradient.
With a gradient, but some of it's bound. I mean, some of it is one would call part of the Earth in that it doesn't have enough angular momentum to stay in orbit, and as it cools and its density goes up, it will collapse onto the Earth. And it's only got the radius that it has at this moment because it's so underdense. So this is a pressure-supported atmosphere initially, and as it cools, it will collapse onto the planet. And out here is a rotationally supported atmosphere that as it cools will stay in orbit. Okay. So that's the distinction here. Those would separate into then the Earth, ignoring any atmosphere because we just assume all the silicate atmosphere collapses, and a disk. So then you would end up with a distinct Earth and disk as it cooled. And then in the post-impact planet, and Dave Stevenson's student presented some of this type work at LPSC this year, where the post-impact planet and the Canup style impacts also leaves you with a very strongly stratified planet in entropy. And they were trying to address whether or not these outer layers and inner layers would mix on the timescales that you need while the disk is still around. So that part is also not clear and hasn't been included in any of the previous work. So the Pahlevan and Stevenson 2007 paper did not take into account the time it took to remove this entropy stratification in their estimate of mixing with the disk.
So I guess I'm still confused, right? Because that's not really entropy, it's entropy density. Don't you care about an entropy gradient?
This is entropy, and then it's the entropy gradient that you'll care about for convection. Yes.
But that's not isn't that entropy gradient
No, this is entropy.
per unit mass?
This is specific entropy. No, this is entropy. This is entropy. Isn't this entropy? This is the units I always use for entropy. But everything in Shockwave stuff is specific.
Yes, isn't that what we mean by density?
No, I don't know what you mean by entropy density. This is
per unit mass, right?
this is entropy. Isn't this entropy? But isn't this entropy?
What's entropy is?
Because energy is PdV plus TdS, right? If you want to get that to have units per kilogram, I think you have to divide by mass.
These are the units I always use for entropy. But these.
Entropy is joules per Kelvin.
So this is specific entropy, which is what we end up using for everything.
But that's extensive entropy.
Yes, but this is all.
Right? Yeah.
Sure, but this is all the same material out here, so does that matter?
The chemistry teacher is not the same material.
Professor, there's nothing wrong with entropy per unit mass.
No, but if you care about whether it's going to convect, don't you care about the entropy gradient rather than the entropy density gradient?
No, I would think it would be the intensive property that you care about.
I don't do convection.
I'll think about this.
There will still be a difference because there's a phase difference between them. So at minimum, there's an entropy difference related to.
What you're saying is that if you remove the mass from it, you don't get the right.
Right, I guess entropy
well,
density is going up so much because density is going down.
Tremendously. This is log. This is
That's
log.
why entropy is so high with it. The density is low.
Well, it has to do with temperature too, right? A lot. Energy.
But it's all hot.
Right, there's P in here folded into here, but in terms of how well you're going to mix afterwards, there's still some work that needs to be done to understand this phase. Okay. Now, during the impact, most of this energy is deposited in the impacted hemisphere. And so here's a color-coded scheme. These are, again, reservoirs of, this is the core, this is the mantle, this is the silicate vapor atmosphere and the disk in colors. And I just arbitrarily divided the mantle into two layers, a lower mantle and an upper mantle layer, just to see where the material came from. And so here's where the material originates. The red are particles that escape the system. Okay. And so most of the material that ends up in the atmosphere and disk are from the impacted hemisphere, which is what you would expect. And most of the material that ends up in the lower mantle originates from the lower mantle of the antipode. Okay. And so even though this code is quite simplified, to first order you could say that the Earth was not fully mixed as a result of the impact. Although SPH does not do a good job of doing fine mixing, especially when you have a very low resolution to your problem. But to first order, if there were slightly different composition in the lower mantle than the upper mantle, you wouldn't have wiped it out. You would have diluted it, but you wouldn't have wiped it out in this particular simulation. Now, the reequilibration of the planet happens on the time scale of hours, reequilibration back into a oblate spheroid, and that does not capture the complexity that would be there if there were a solid lower mantle and a magma ocean, say, as your pre-impact state, or if your whole planet were solid and you only melted part of it, in that the contrast in the flow properties between the two are not captured in this reequilibration. And that could also aid in the preservation of lower mantle chemical signatures through a moon forming process. Okay. I should tell you the bit about the angular momentum. So we did not model the formation of the moon. We modeled the formation of the disk, and it has enough angular momentum and mass to make a moon under reasonable assumptions, but that has not been modeled by anybody yet for these very vapor-rich disks.
So even Canup?
No, I mean, her disks are all colder. that style because it's only 10 kilometers per second, and much of that material was injected via torques instead of through this big blowout half the hemisphere of the planet process. Those models are improving, but there's a lot of room for improvement there. So after one forms the moon would form just outside the Roche radius, is the idea, and quickly once the disk cools down. And then the moon begins a tidal migration with the Earth, so its orbit is going to continue to expand. And at some point during that expansion, not far outside of the Roche radius, there is a resonance between the precession period of the moon and the Earth's orbital period. And so the orbital period of the Earth around the sun at a year and the rate at which the perigee point precesses becomes a year. Okay. When that occurs, there is a resonance called evection that fixes the precession of the lunar orbit at 1 year. And because the precession period of the orbit is locked while it's captured in resonance, that limits the evolution of the semi-major axis and eccentricity of the moon and limits the angular momentum that can be absorbed by the moon. So what happens is throughout this process, the Earth is transferring angular momentum to the moon via tides, just normal Earth and moon tides. But at some point, the moon cannot absorb the angular momentum because it's locked in this resonance, and then it transfers the angular momentum to the Earth-Moon-Sun system and moves the Earth's orbital period ever so slightly longer. Okay. So there's an animation of this process here, and this is again top-down view. The sun is always in this direction. This is the Earth, and this is the lunar orbit. So the red line will evolve, and these are Earth radii again. And so the Roche radius is about 3 Earth radii, and here he's starting the simulation just a little bit past that with a fully formed moon, a little bit past that, and it will expand outward and get caught. So it's expanding outward, gets caught in the resonance. That fixes. This is in the reference frame where the perigee is always fixed from while it's in the resonance. The semi-major axis expands, the eccentricity expands, reaches a plateau, and then shrinks as angular momentum is being dumped onto the sun. And so here it breaks resonance, and the resolution, let me explain for a second. The jitter that you see at the end is the fact that the time period that was output to make the movie no longer resolves the precession of the moon orbit. So it looks jittery, and it's just because it's an under-resolved orbit. And so now look at, we started with a planet that had 2.3 hour spin. It's slowing down, and the total angular momentum of the system is decreasing as it's locked in resonance, and angular momentum being transferred to the moon can't be absorbed to the moon and gets dumped onto the sun. And then it breaks resonance when basically what happens in these simulations is the Earth slows down, the Earth spin slows down such that the tidal bulge, the tidal forces on each body become comparable at closest approach. And that's when it ends up breaking resonance under these assumptions. And so here he found the parameters that could let you exit the resonance at the right point, and ran a whole bunch of different simulations where he began with a system with different total angular momentum. These are 2 1/4, 2.5 hour initial spin periods for the Earth, and then there's tidal evolution outward, capture into resonance, and then breaking of resonance and normal tidal evolution afterwards. And the time scales here are these tens of thousands of years. So
this is kind of curious, actually, right? That you always end up.
No, it's not always. No, it's not curious.
The current value. It's a complicated 3-body problem. Right?
So dynamics is one of those non-invertible problems, right? And so if you think that a system went through a resonance, then you know where it lost resonance, and you can calculate what conditions give you losing resonance today. So there were plenty of other solutions where one did not exit at the present day value. Okay. But you cannot tell how you got caught into the resonance. Okay, and so then when I asked Mattia, why hadn't this been done 20 years ago? And no one had considered his conditions for getting caught into resonance. The people who named the resonance, Tumra and Wisdom, had started with just a little bit above the present angular momentum, got caught into resonance, but then quickly broke the resonance because they were already near the present value. And so they didn't think it did much. And Robin has told us that she looked for different ways of losing angular momentum in this resonance. And there seems to be a parameter space of how the tides on the two bodies interact with this highly oblate Earth that lets you get caught in the resonance long enough to dump angular momentum. Now, this is, I have what the requirements to break angular momentum are special, and in a sense they define the tidal parameters of the two bodies if you think it went through the resonance. And you have to decide if those are reasonable. So this is just what we think is happening. So now we're adding the constraint. I want to get to issues. The present day angular momentum has to be satisfied somehow. The mass of the moon, low iron content, the isotopes. But we're proposing that we start either with a faster spinning system or that the total angular momentum of the impact reaches the point of fission, essentially. Small impact or more reasonable impact velocities. The impacts are more head-on, which is less likely, but the range that had reasonable solutions were large enough that that's okay, and that you lose angular momentum through this resonance. And there are many, many aspects of the problem that are hard for all giant impact models of the moon. The first being for the equations of state that we're using are quite simple. We're modeling the whole mantle as a Forster-Wright idealized EOS, a pore model for iron. And in this case, with the higher impact velocities, the disk is mostly vapor, and we know that these models are poor around the vapor dome. And thus, we need to improve the EOSs, which we're working on experimentally. And then, do we really expect such high angular momentum impacts? The current N-body simulations say yes for the standard way of forming planets, but there are new models for forming the Earth that may not lead to such high angular momentum states. The tidal models are quite simple, and now we're dealing with an oblate Earth that has this high J2. It's not being captured perfectly in the models. The Qs are assumed to be constant, the tidal quality factors, the tidal lag doesn't vary. These are all things that can be improved in the models. And to break resonance at the current angular momentum under the model assumptions, the Earth and the Moon need to have similar Qs. Both planets are likely partially molten, and how different the Qs vary by orders of magnitude with small differences in rheology, and so it's not clear if this will work, and so people are going to work on this part of the problem as well. And then, so we think one could explain the isotopic signature of the Moon by impact-induced fission. If the Moon was spinning quite quickly, it would have probably been spinning quite quickly for a fraction of the end stage of planet formation. Fraction could be tens of millions of years. The end stage of planet formation, that would affect pattern. Now you can't ignore rotation, I think. Now we have a very fast rotating planet, and it would affect many processes during the end stage of planet formation. The high angular momentum events are only the giant impact stage. They're not the runaway growth, they're not the oligarch stage, they're just the end stage of planet formation. And then if the simulations, as they suggest that the energy of the impact is shallowly deposited, then you could preserve the signature of heterogeneous accretion, which is what the noble gas isotopes say, and then tungsten says something, but I don't quite know what. And then the way that the message I'm trying to send to the students this week is that you don't fully homogenize the Earth in giant impacts, but there's quite a lot going on at the same time.
You gave me this talk again?
No, I'm giving a more general talk that's not so focused on the one problem. The impacts talk, I was planning on talking about more about impacts in general and the stages of planet formation and the thermal perturbation part that's not well known. And the moon is the best example because we have data.
I'd love to see some of this again, just because.
There is a paper you could read.
This one.
Yes, it is in review. So we'll see what happens. And there is a paper on general aspects of the giant impact stage of planets that came out in APJ earlier this year.
So how does your model explain the high degree of volatile depletion and low Fourier reducing conditions on the moon?
So I know nothing about oxidation states, but the high temperature origin, the way that I envision what's happening, even though we don't have a very good model for the disk, is that the moon is accreting on the outer edge of the disk, because that's where the material is cooling the fastest and condensing. And you've got to think of this as not a single stage process. Basically, material is cooling and leaking out of the disk. But the whole disk is essentially one composition, except that now you're taking the high temperature condensation portion of it and putting that into the moon and leaving the volatile component in the disk longer, and that mass ends up being accreted to the Earth preferentially. And so in the N-body simulations of moon formation that don't include phase changes, so just starting with all condensed material, what happens is when about half the mass has gone out to form the moon is now a significant torque on the remaining disk. And so instead of more mass leaking out onto the moon, the torques transfer angular momentum to the moon, and the rest of the disk collapses onto the Earth. And so that's a very easy way to have volatile, more refractory separation. And the moon is then forming out of condensed material. It's not a boiling planet. It's the opposite of the boiling part, right? It's the condensed fraction leaking out. It may be solid. Those clumps that leak out may cool quickly. So this question of did the moon form fully molten or not, I think is also something that will have to be addressed with these more sophisticated disk models.
I guess I don't understand why or what is implied by stratification of specific entropy.
Well, I was trying to make an argument against instant mixing. Instant mixing. I can convert all of this to per joules per gram, joules per Kelvin.
That's right.
I'm just trying to say that it's not at the hours, the day afterwards, it's not fully communicating through the whole planet.
So stratification of specific entropy implies compositional stratification?
In these models, there is no compositional stratification.
So it implies...
It implies entropy stratification. But there is a compression term that would need to be taken into account, I think, to get to the number that you care about. But I can pull that out.
No, I think that's right. So
Does it imply there's no convection?
Yeah. Right.
Immediately afterwards, it's temporarily stable. And the question is, how temporary is that? Because if you wanted to communicate with the moon, with the disk, you only have so much time.
100 years.
It's order 100 to 200. So the question is, how quickly does the Earth start convecting, and does it do it in a way that quickly mixes the whole of the...
So can you get a Rayleigh number from the gradient in specific entropy?
I can't, but he can.
Okay.
Okay.
I could learn how to do
this.
this.
Stratified, you probably would want to identify different subregions and see whether there may be some areas, in fact, that can still convect.
Right, and so now it's just that you're not considering right, you can't just have one number for the whole system. And
the mantle part of that planet may be able to convect.
A portion of it may be able to convect, and but then you have to add the extra complication of whether or not it's solid, liquid, or fully molten.
The entire mantle or just
the scale was so saturated.
Right, so
The mantle.
we can do a lot better. I've been trying to figure out how to handle an equation of state that knew about perovskite and olivine, say, as a better step forward to try and come up with a more realistic division of energy, because right now these are all somewhat biased in their shock energy deposition from the simplified EOS. So at that point then would be a good point to look at what the post-impact stratification really is and what layers could easily mix or not. Dave at LPSC during the pre-conference workshop, the Brown Symposium, was looking at Kelvin Helmholtz sensibilities to initiate mixing, which might be one way to.
In the mantle.
In the mantle.
Reynolds number is never big enough in the mantle.
I
Maybe
think
the
that's what he
simulations
said.
may well be, but the viscosity of the mantle is way too high to get Kelvin Helmholtz instabilities.
Well, this is not the mantle. I mean, this is some other beast entirely. This boiling silicate material. I'm still worried about starting with solid earth and not fully melting the lower mantle. That alone gives you a big viscosity contrast, and whatever is partially not fully melted is stuck as a layer at the bottom, and it's very hard to get it to do anything. And given the energy deposition, if the lower mantle is solid, I think it is very hard to get it all melted the whole way through. But we're going to work on that specific problem as best we can soon.
But can't you also turn the problem around and say, well, we know that there are heterogeneities based on xenon and tungsten isotopes that tell you if they're homogenized?
Yeah.
Right. So the new data clearly guided our work on.
Even without those helium isotopes telling you that it's not homogeneous.
No, but the helium isotopes don't tell you whether it was homogeneous
Earlier.
Right. Right. So
It was not homogeneous.
today. That's right.
Right.
So you need the extinct nuclides to tell you whether it was homogeneous or around.
And so we have an issue with planet formation in general with the moon, because if you want things like tungsten, all these systems that become extinct to be the same on the Earth and the moon, the easiest way to do that is to have the moon form late. But that means that you had to preserve the heterogeneity in the mantle as you form the moon. Not totally wipe out the heterogeneity is the better way to say it. Not preserve them as they were, but not totally wipe them out. Yeah. Everybody needs